For over 2,000 years, geometry has been shaped by one name, Euclid. In the bustling city of Alexandria, around 300 BCE, Euclid wrote his influential work, The Elements. In it, he laid down the very building blocks of geometry, 5 fundamental postulates. These postulates have guided mathematicians and scientists for centuries, defining how we understand space, shapes, and their relationships. Geometry existed long before Euclid, with roots in the civilizations of Egypt, Babylon, and Greece. But it was Euclid, a Greek mathematician working in the Library of Alexandria, who formalized the principles of geometry in a systematic way. His masterpiece, The Elements, became the most influential textbook in history. At the heart of Euclid's geometry were five simple statements, his postulates. From these, all other geometric truths could be deduced. So what were these 5 postulates? The 5 postulates are axioms. Postulate 1. It is possible to draw a straight line from any point to any point, as shown here. Axiom 2. If you have a straight line, it is possible to extend in any direction to infinity. Postulate 3. It is possible to draw a circle given a center and a radius. Postulate 4. All right angles are equal or congruent. And now finally the 5th parallel postulate, which is a little bit more complicated. It says if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than the 2 right angles. The best way to understand this is with some pieces of uncooked spaghetti. So, as you see, we're going to put 2 strands and put them face leaning towards each other and lay a 3rd strand across the first 2. You see you've created 8 angles of which the 2 intersections, 8 angles at the 2 intersections. Look at the same side interior angles toward the closed ends of spaghetti. The sum of both the same side interior angles is less than 180 degrees. So Euclid is saying the lines represented by the first 2 spaghetti strands will, if extended indefinitely, meet. Let's draw the parallel postulates. So take a sheet of paper, pencil, and a straight edge. Draw a short line, perhaps 10 centimeters long. Move away a few centimeters from it and draw another 10 centimeter line. Now draw a transversal line crossing both of these first 2 lines. If the 2 interior angles on the same side lead to less than 180 degrees, the drawn lines will, if continued, meet. Try it. See? Now, if they will meet, now start again. But this time, draw 2 parallel lines when you draw in the transversal. The 2 same-side interior angles will either be exactly 90 degrees or will be a combination of an acute and an obtuse angle. For any line and a point not on that line, Euclid shows us that the only one line can be constructed through that point that will be parallel to the line. All other lines will eventually intersect with the original line. Euclid's parallel postulate allows that transversal to create many different angles as it cuts across the 2 lines. But it all boils down to only 3 possibilities. The lines are not parallel, and 2 same-side interior angles are less than 180 degrees. The lines will eventually meet on that side of the transversal, as shown there. The lines are not parallel, and 2 same-side interior angles are greater than 180 degrees. The lines will never meet on that side of the transversal. The lines are parallel, and any 2 same-side interior angles will be equal to 180 degrees. The lines will never meet as long as the 2 interior angles on the same side of the transversal are less than 180 degrees. The simplicity of Euclid's postulates is part of their genius. From seemingly self-evident truths, such as the idea that a straight line can be drawn between any 2 points, emerged a universe of discovery. His work has influenced not only mathematics, but also fields like architecture, engineering, physics, and even philosophy. The axiomatic method he pioneered, building complex systems from basic principles, remains a cornerstone of logical reasoning and scientific inquiry. What is truly extraordinary is how these postulates have withstood centuries of scrutiny. Despite revolutionary advances in science, from Newtonian physics to Einstein's theory of relativity, Euclid's framework remains relevant. Even as non Euclidean geometries emerged, challenging some of his assumptions, they did not diminish his work. Instead, they expanded it, showing how foundational truths can inspire entirely new dimensions of thought. Euclid's legacy reminds us of the power of clarity, rigor, and intellectual curiosity. His postulates are not merely historical artifacts, they are a testament to the enduring pursuit of understanding, a journey that connects us to the great minds of the past and propels us towards the future. So, as we reflect on Euclid's contributions, let us marvel at the beauty of ideas that transcend time, proving that human ingenuity knows no bounds. Euclid's postulates laid the foundation for millennia of mathematical thought, proving that sometimes the most profound truths come from the simplest of ideas. Euclid might have been known as the greatest mathematician, but in reality he was the father of many fields. We are reminded that geometry is not just about shapes, it's about understanding the very fabric of our world.